A confirmation about the audio, please, guys. If the audio is clear and audible, thank you. So, hello, good evening to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to the session of oceanography, where we shall be moving ahead from the portions where we left off. Yesterday, where we started the portion of oceanography, we had initiated the discussion about the ocean bottom relief, where we discussed certain features of the ocean bottom relief. We discussed the genesis and the formation of these features to be attributable to the geomorphic processes around us. And that is how you basically have a variety of either tectonic features or volcanic features, or the erosional and the depositional features are the ones which end up dominating. So basically, we saw the examples of each one of them as well. And then we moved ahead for the classification and the division of the ocean floor, where for the ocean floor, we basically observe four major classifications: continental shelf, continental slope, the abyssal plains or the deep sea plains, and the oceanic trenches. These were the major divisions of the ocean floor. And then you had the minor ones like the ridges, seamounts, goyards, etc. Trenches, canyons, these are the minor features of the ocean floor. We observed what a continental shelf is. We basically looked at the continental shelves and we basically observed their property, that they are basically created as a consequence of the depositional process, where the depositional processes from the land masses nearby end up creating that extended part of the continent underwater, that is the continental shelf. Now, continental shelf is not very deep, which means sunlight is able to penetrate there. And if sunlight is able to penetrate, that basically means that there is going to be presence of marine plant species, and presence of marine plant species accounts for a greater incidence and concentration of biodiversity. That is why we come across a situation where the continental shelves, even though they occupy only around 7 to 10% of the oceanic area, they end up representing close to around 90% of the oceanic biodiversity. It is here that in many of the regions, you even find the presence of fossil fuel. Now, the continental shelf basically ends at the shelf break. That is the end of the continental shelf. If the continental shelf goes on like this, it eventually ends at the shelf break, where suddenly it starts getting very deep. And beyond that, the slope suddenly increases, where the depth of the water beyond the continental shelf area can increase from around 200 meters to around 3,000 meters or 3 kilometers below the sea level. So the continental slope is a region of steepness and a significant amount of depth. Then we also studied about the submarine canyons, where we observed the formation of these canyon-like structures. They are a resultant of two processes. Basically, a resultant of the process of erosion, but that erosion can be caused by two of the reasons. One, mouth of the larger river. Let's suppose a large river flows from here. So that large river will carry the sediments, the sand particles, etc., which will rub against the sea floor and eventually create that erosional structure. So that is one of them. The other one is basically the turbidity current. Whereas the sea wave action continues to happen, the sea wave from the coastal area tends to have that sliding down of sediments, clay, sand, pebbles, rock, gravel, everything basically starts sliding down the continental shelf, the sea floor. And in certain areas, there will be more of that movement, creating that depression, which we refer to as submarine canyons. Submarine canyons can extend from the region of the shelf to the region of the continental slope and beyond. Then we now move on to the deep sea plains. Deep sea plains basically is the large, significantly larger, almost flattish plain at the bottom of the seafloor. Just like how you have the plains on the ground surface, similarly, these are large plains at the bottom of the seafloor. These plains are on an average at a depth of around 4 to 6 kilometers from the sea surface. So you can imagine that these plains at the bottom there, you will never have the availability of sunlight. Sunlight concentrates only in the topmost layers, up till a few hundred meters, maybe, not beyond that. So, this is a region that is a deep sea plain or the abyssal plain where sunlight has not reached for millions of years, basically, in these areas. And these are the regions of almost consistent temperature, consistent salinity, consistent pressure. Because regardless of heating from above, cooling from above, wind direction from above, evaporation, rainfall, anything which happens on the ocean surface, it will impact the ocean maybe at a depth of up till around from the surface to around 100 meters, maybe around 200 meters, or sometimes even up till 400 meters. 400 meters from the surface is also a significant amount of water that we are talking about. But underneath that, beneath that, you have a consistent maintenance of temperature, salinity, pressure conditions, which is isolated from the atmospheric condition or the atmospheric influences. So that is the case of these deep sea plains. These are what are also referred to as abyssal plains. Abyssal plains. For a long period of time, it was thought that because you did not have the presence of sunlight here, so obviously plant species won't be observed. And because plant species won't be observed, you won't have biodiversity. It was basically presumed that this region would be lifeless. But few of the recent expeditions have indicated something very different. Here, you have a unique set of species which have adapted to living a life in that permanent darkness. You have certain species of fishes, certain species of sharks who have basically adapted to the life of perpetual darkness. They have larger eyes, stronger heads in order to withstand the pressure. Such species living at the ocean bottom, they are known as the benthic species or the benthos. Species living at the ocean bottom. For a long period of time, they did not, or there was no living species living in the, as the scientists presume, basically, that for a long period of time, when life came into existence in the oceans, the deeper part of the oceans were never inhabited. The deeper part of the oceans continued to not support life. It was only when the coastal areas they faced certain threats and you had mass extinctions which happened in the coastal areas, due to which you had a series of various aquatic animals basically dying at the same time and depositing themselves over the continental shelf region. That is when it is said that many of the species they escaped into the depths to survive, and they have been surviving ever since. So that is why there is a great amount of unknown about these ocean depths and the ocean bottoms, for which a greater amount of discovery, a greater amount of research is actually required. Then we have the oceanic deep or the oceanic trenches. How are these oceanic trenches created? No, crabs are not benthic. Deep Shikha Uh, Deepshika will take a look into it. Send it over to me. So, how is it that the trenches are formed? Oceanic convergence. Very good. Molten materials come out. No, don't get di- don't get disturbed by the image here. These are the oceanic trenches. So, oceanic trenches are created due to convergences. Oceanic convergences. These oceanic convergences can be of two types. You can have ocean-ocean, ocean-continent. Example of an oceanic trench formed due to ocean-ocean. Mariana Trench. Very good. Example of an a trench formed due to oceanic continent convergence. Peru, Chile. Good. So these are the deepest portions underneath the ocean surface, where, for example, the depth of the Mariana Trench is going to be somewhere around 11 kilometers from the ocean surface. So think about it, 11 kilometers from the sea surface. Mount Everest is 8.8 kilometers higher from the sea surface. Mariana Trench is around 11 kilometers deeper from the sea surface. So there is a significant amount of depth, and many of these areas remain unexplored. Now, this is the broader schematic of what you observe in the case of the ocean relief or the ocean bottom, where you observe that along the coastal areas, the water is shallow, it is not very deep. This is the shelf area. Then suddenly the depth increases, then comes the slope area. Then you have the deep sea plain or the abyssal plain. In between them, you might have few of the volcanic islands or sea mounts which might exist. On the other side, you might have another oceanic plate here having a continental shelf, slope, a rise, and an oceanic trench. So this is clearly an example of oceanic convergence. Okay, right now. Checha Peru Chile Trench is oceanic continental. Yes, we have written here oceanic continental Peru Chile. Now, after this, we come to the portion of ocean temperature. What is this ocean temperature? How is it that this oceanic temperature tends to vary? So, when we talk about ocean temperature or the temperature in the oceans, you have to understand that any ocean or the water, what is the source of heating for these waters? What is the source of heating? It is basically the solar insolation, the sunlight. Sunlight is the main source of heating. So generally, we will come across the fact that temperature on the surface is generally on the higher side and it reduces as you go to the depth. Okay, you have colder waters at the depth. But then temperature varies. Temperature of the oceanic areas, let's suppose in the equatorial Indian Ocean, will be very different than temperature of water in the North Sea or the Norwegian Sea. Right. So temperature tends to vary from latitudes, whether we compare the temperature of, let's suppose, the Mediterranean and at the same latitude, the Atlantic Ocean. Let us suppose if we compare the temperature of Mediterranean and Atlantic Ocean at the same latitude, Will they represent similar temperature or will they represent a difference of temperature? If similar, why? If different, why? Mediterranean and Atlantic. At same latitude. Similar temperature, yes. Why? Different temperature, why? Very good. At the same latitude, Lakini, how will the angle of solar rays be different? Good. Few of you are absolutely correct. Vibhu, Brajneet, Rani, Dikshit, Ankush, Shreyas, Sakshi, Anjan. Very good. Many of you are saying different because of depth. Depth, why will it influence the surface temperature? Pihu, correct. Basically, it varies. The temperature varies because Mediterranean is surrounded by land masses. Being surrounded by land masses means what? It means that there the impact of heating will be much more prominent. And because of that, the Mediterranean will be much hotter. So basically, temperature across different regions, they tend to vary. Okay, so they are dependent on many of the factors. Let us take a look into them. First of all, prime source of heating is the solar energy, heating by the sun. The process of heating and cooling of the oceanic water is slower than the land. So land heats up more faster, land cools down much quicker as compared to the ocean. Now, what are the factors based upon which we observe varying temperature on the sea surface in different areas of the planet? So here, factors affecting the temperature distribution in the oceans. Here we are talking about horizontal variation in temperature. Horizontal variation in temperature. So, one is the impact of the latitude. So, surface water temperature decreases from equator polewards because of insolation, the solar insolation which is received. Right. So, we do know that with different latitudes, the amount of insolation changes. You have greater amount of insolation received at lower latitudes, lesser amount of insolation received at higher latitudes. So that is why higher latitudes are a bit cooler. So that is why higher latitudes will have lower temperature. Once you have read the portion of climatology, this should be pretty easy. Higher latitudes have lower temperature. Then after that, unequal distribution of land and water. Now, the predominance of more amount of land in the northern hemisphere does impact the process of heat gained and heat lost by the water body. Okay, please understand, when we say a water body is cold or air is cold, this is a kind of a science, simple science basically. When we say that water is cold or air is cold, cold or coldness is not a form of energy. It is the lack of heat which makes an object colder, right? When you don't have enough heat energy present in an area, that is when the region becomes colder. As simple as that. It might seem to be similar, but there is a massive difference between each of them. So when we say colder areas, they don't receive that much amount of heat. So the proximity of the land masses nearby, they will always tend to influence the heating or the cooling. For example, in the case of Indian Ocean Dipole, we did come to the conclusion and we did observe that the Horn of Africa and the region of Arabian Peninsula, when they get heated up, they will basically end up heating the waters close to the Western Indian Ocean and the region of Arabian Sea as well. Right? So that basically, on an average, brings about a greater amount of fluctuation in the oceanic temperature in the northern hemisphere as compared to the southern hemisphere. So oceans in the northern hemisphere has more contact with the land compared to southern hemisphere. So in total, more heat is received. Now, then the prevailing winds, the existing wind types. Now, we have already studied about upwelling and downwelling in significant detail, isn't it? We have studied about, I hope that till now it is recalled. Gunjan, geography will continue for how long? Gunjan, you can end the pain whenever you want, my dear friend. You can make it the last session whenever you want. There is no issue in that. But mostly by next Thursday or Friday, we should wrap it up. So prevailing winds basically means the winds in existence. In existence over a region. These winds can be onshore. These winds can be offshore. Now, how do they make a difference to the sea surface temperature? So we have seen basically that, let's suppose here you have the water. Let's suppose. Now, if there is a strong wind moving in this direction, it will pile up the surface water. It will pile up the surface water, and eventually that surface water will be pushed down. That is what we refer to as downwelling. Now, what is the impact on sea surface temperature due to downwelling? The sea surface temperature, very good, will increase. So, because there is a piling up of this warm water, so during downwelling, up of warmer surface water, for a detailed definition, etc., we have already covered it, I think, in module 10 itself. So you can take a look at the detailed definition from there. You can take a look at the recordings from there also about the downwelling portion. So warmer surface water. Now this piling up, so suppose if a wind is moving like this, if a wind is moving in this direction, it will drag all the surface water along with it. Eventually, that surface water will be brought down. That surface water will be pushed down eventually. And that pushing down of the surface water, because where will the excess surface water go? All the winds from the ocean surface, they are bringing that warm water. Where will that warm water go? For example, if you take a look at the portion of the map of the Pacific here, if you can kindly concentrate in the region of the Pacific, we have studied the Walker circulation, the Enzo cycle. So this is something that you should be able to associate with. So observe how the winds here, they are carrying the water from a direction of east to west. All that water comes to the Western Pacific, the warm water. Now, where will the warm water go? This warm water eventually, It cannot flood Indonesia, Philippines, Australia, etc. So where will it go? It will eventually be pushed down. After getting piled up, it will eventually be pushed down. So because of this, you have a significant accumulation of the warm surface water in this area that leads to a raise in or increase in temperature. Then the opposite of it is what is observed in the case of offshore winds. Let's suppose you have the region of an ocean. Now, if you have the movement of winds in this direction, let's suppose movement of winds in this direction, then what happens? Then basically, as the top surface is carried away, then from the subsurface, the colder waters rise up. This is what is known as upwelling. Now, what is the impact on the surface, sea surface temperature due to upwelling? Here, subsurface water rises up. Again, out of upwelling and downwelling, which of them is suitable for the fisheries, for the fishery sector? Which of these phenomena will be beneficial economically for the fisheries sector, upwelling or downwelling? Beautiful. Always upwelling. Because upwelling will bring nutrients from the deeper waters closer to the surface. Using these nutrients, phytoplanktons will grow in population. These phytoplanktons will eventually feed the marine food chain, due to which the fish population is going to increase. Then you also have the role of ocean currents in terms of influencing the oceanic temperature. Now, here, ocean currents we will study today itself in the later part. But basically, just to understand it, just understand that just like in the case of the surface temperature of the landmass, during studying about climatology and the portion of atmosphere, we had studied that cold advection and warm advection happens. Cold advection means cold winds come to an area, it lowers the temperature. Warm advection, warm winds come to an area, it heats up the region. Right? Similarly, ocean currents also, as compared to their surrounding waters, they can either be colder, they can either be warmer than the surrounding waters. If let's suppose you have a warm ocean current coming into an area, that will raise the temperature of the water body in that area. Conversely, if you have a cold ocean current prevailing in an area, that will lower the temperature. So warm ocean currents raise the temperature of cold areas, while the cold ocean current decreases the temperature. Let me show you the example of this with the help of an image. Let me go to a better image. This image. Now, first of all, observe across these areas, these latitudes. Across these latitudes, if you observe the temperature difference, you will observe warmer waters here, isn't it? Now I hope you can focus here. Warmer waters in this region. Why is it that here water oceanic temperature is higher? Heating cannot happen here. We are talking about 60-70 degree latitude. We are talking about the Arctic Circle. But why in the Arctic Circle you have warmer waters here? Because of a warm ocean current in the name of North Atlantic Drift. Here you have a warm ocean current in the name of North Atlantic Drift. That is why. Now, again, I want you to look at this image a bit carefully. Okay, a bit carefully closer. Observe this portion, this particular portion. I will erase it, the marking. I want you to observe that portion. I hope you are able to observe some tinge of cold water here, some bluish coloration that you observe here. I hope you are able to observe that. Yes? Good. Now observe the water at the same latitudes, everywhere at the same latitude. It is warm. Again, here you will observe some tinge, but it is warm everywhere. Here it is cold. Why? Because you have the cold California current coming into that area. Cold California current. Then again, around the region of equatorial Pacific, you will observe the accumulation of these warmer waters. Here the waters are colder in comparison to this region. Here you will observe water is colder as compared to the same latitude. While there is upwelling in action in this area, you also have the presence of Peru current in this region, the cold Peru current in this region. So like that, ocean currents will end up influencing the temperatures, right, of an area, just like advection would influence the temperature of the surface in one region. Like that, ocean current also influences the temperature in that area. Okay, so basically here you observe, for example, these ocean currents, you have the cold ones on the western side of the continents. Almost all the western side of the continents will have a cold ocean current. We will come to the reason also. There is a climatological reason behind it. But here, this warm waters of North Atlantic drift, these warm waters keep these seas ice free. Even during winter months, you will have a lot of chunks of icebergs, etc., but still relatively it is not completely frozen. Ships can move without an icebreaker. So it is this North Atlantic drift which allows trade, very and much important trade, from the oil bearing regions of Scandinavian coastline and North Sea for the remaining portions of the world. So that is why these ocean currents, they are very, very helpful in that matter. Now, then, here you can give and cite various examples. Examples I hope you can cite. North Atlantic drift, warm. Drift, warm. California current, cold. Then, at the same latitude also, it is not as if the temperature is going to be consistent. Whether you talk about an open ocean like an Atlantic, observe the Atlantic. Atlantic is quite open from the north and the south, right? As compared to, let's suppose, a Mediterranean, which is enclosed, or let's suppose a Black Sea, or let's suppose the North Sea, or let's suppose the Gulf of Bothnia, or the Baltic Sea. So these are your Red Sea, for example. This is enclosed, isn't it? So when you compare the temperature of an enclosed sea or an open sea at the same latitude, there will be a difference. Difference created because of the heating of the land nearby. Because in the case of the open oceans like the Atlantic or like the Pacific, you will have a uniform variation of temperature as the water tends to lose heat with the latitudes, a uniform variation of temperature. But when we talk about the enclosed seas like the Mediterranean, the Red Sea, the Persian Gulf, etc., the Arabian Sea, the Bay of Bengal, heating of the nearby land masses will influence the temperature. Or in this case, of let's suppose the Baltic or the Gulf of Bothnia or the North Sea, cooling of the nearby land masses, because the land will cool down very immensely as well at a very tremendous pace as well. So, cooling of the land masses will make these enclosed seas much colder as compared to the open ocean. In the lower latitude, heating of the land masses will make these enclosed seas much hotter as compared to the open ocean at the same latitude. For example, observe the Bay of Bengal, right? Compare the same region with Atlantic at the same latitude. Bay of Bengal will be much hotter. Why? It is closely surrounded by land, right? So the warming of the land, the heating of the land will heat up the water quite sufficiently. So at lower latitude, the region of the enclosed seas will be much warmer because the land is going to be hotter, right? Land will gain heat much quickly, so it will heat the water bodies. Then, when we talk about the open oceans, there the temperature variation will be very uniform. Lower latitudes around equator, high temperature, higher latitudes, low temperature. But the enclosed seas, again, let's suppose the Baltic, the Gulf of Bothnia, North Sea, Kara Sea, etc., in the very higher latitudes closer to the poles, the land will get so cold so very quickly. These enclosed seas will, in fact, become much colder than the Atlantic or the Pacific at the same latitude. I hope that is understood. So basically, here, when you compare the open seas or the enclosed seas get significantly. Let me first of all divide this into lower latitude and higher latitude. So lower latitude gets heated significantly due to the influence of the surrounding land. In the higher latitudes, get much colder. The enclosed seas will get much colder due to the cold landmass nearby, and that hotness or coldness that is transferred to the water by the process of conduction. Initially, by being in contact with that hotter landmass, the water starts getting hotter, and then by the process of convection it is spread into the surrounding area. So conduction and convection, these are the process which spread the heat. So at low latitude, enclosed seas have higher temperature as compared to open oceans, and at high latitudes, open seas have higher temperature, enclosed seas have lower temperature. So here, if you take a look at this map, you will observe significant amount of variations. One thing that you will notice straight away is the fact that in the northern hemisphere, there's quite a different kind of a pattern in terms of distribution of temperature. There is no such uniform pattern, something that we had seen even while studying the isotherms, if you remember the isothermal images. So here, you have altogether the presence of different patterns. In the southern hemisphere, you have a very uniform distribution of temperature. Temperature varies from one latitude to another very uniformly. Okay, so there is that amount of cooling which happens from one latitude to another. Now, here also observe, we can see from this image that Arabian Sea is much wider and Bay of Bengal is much narrower, due to which Bay of Bengal will get heated very quickly. And when Bay of Bengal will get heated much more quicker as compared to Arabian Sea, which atmospheric phenomena can be observed or can result from that? Let me know. Very good. A tropical cyclone. So this is one of the reasons again why the region of Bay of Bengal experiences greater occurrence and more frequency of occurrence of tropical cyclones as compared to Arabian Sea. It is smaller, gets heated much faster. Now we come to the vertical distribution of temperature. That is, how is it that the temperature varies as you move into the depth? Now, the source of heating is the sun. So going into the depth, eventually the solar rays disappear. Beyond a depth of around a few hundred meters, the solar energy disappears. So when the solar energy disappears, heat will not be present. If heat is not present, then the region becomes very cold. So if you consider, let's suppose water. Let's suppose you consider water to a significant depth. Let us assume this is your sea floor. Now, as this solar energy will enter, surface will get heated up quite significantly. Right. Let's draw a chart of temperature. Let's say this is the graph for depth. This is your surface. Few hundred meters eventually. Let's suppose this is the bottom. And then, let's suppose this is the chart of temperature. 24 is the ideal temperature at the surface. So, let's have this chart of the temperature here also. So, on the surface, let's assume it is 24 degrees Celsius or 25 degrees Celsius. Now, if we come immediately closer to the surface, temperature is distributed by water. Water has got a uniform distribution of temperature. So let's suppose closer to the surface, temperature is consistent. But as we reach a depth of maybe 50 meters, 100 meters, the intensity of solar rays will reduce. So the temperature will reduce. The temperature will reduce. Now, these solar rays, let's suppose they are able to reach up till a depth of around 500 meters from the sea surface. Okay. So in this zone, will I be correct to presume that there will be a rapid decline in temperature in this zone? Because after this zone, you have the region of permanent darkness. No light has entered that area, permanent darkness. But in that particular zone, you have a transition from availability of sunlight at this level to almost disappearance of sunlight at the bottom level of that zone. So there is a significant amount of transition of temperature which will be observed. So here, the temperature decreases or varies very rapidly. Then you enter the zone of permanent darkness, where the temperature is almost consistent in the range of around 3 to 4 degrees Celsius. Okay, so this zone where there is such rapid transition of temperature, that is what is known as thermocline or gradient of temperature. Thermocline. So here also with this image also you can see that sunlight is available only up till this area, and that is your photic zone. Beyond that, sunlight is not available at all, and that is the region of aphotic zone. Okay, so you have the photic zone and you have the aphotic zone. Photic zone basically where sunlight will be able to penetrate. There you will always have slightly higher temperature or influence of the surface climate will be much more. In the aphotic zone, the zones of darkness, there will be a consistency of temperature, consistency of the salt content, pressure, everything will be consistent because the conditions there, they have largely remained the same for millions and millions of years. Okay, so the region, basically here you will observe the variation in temperature from the surface. So near the surface, let's suppose this is the temperature. Then there is that zone of transition where the sunlight eventually disappears. And that zone of transition, that is known as the thermocline. And then again, the temperature reduces almost consistent to around 4 degrees Celsius. But why is it that at the ocean bottom, temperature does not reduce to -10, -15? This is region of permanent darkness. Why is it that the temperature doesn't reduce to -10, -15 degrees Celsius? Can we imagine? Very good, Rani. Madhu, correct. Vibhu, correct. So basically, there are two reasons why the temperature at these depths, they remain consistent around 4 degrees Celsius. But before that, I hope we are aware that the pressure at the bottom is very, very high, significantly and sufficiently very high. That is why the marine species that you see near the surface, they cannot go at the ocean bottom. Their body will simply be squished because of the pressure. The large submarines that the various countries build as a pride to their nation, whenever any of these submarines, I hope we are aware that these submarines have a bottom limit. They cannot go beyond a depth of 400 meters, 500 meters, etc. The deeper ones go to the depth of 500 meters. If these submarines somehow land at the ocean bottom, which does happen in the case of submarine accidents, they virtually get crushed like a Coca-Cola or a Pepsi can that you basically consume and crush it. Like that, the submarines get crushed. So basically, the pressure is very high. When the pressure is very high, water will tend to gain its maximum density. Listen to this very carefully. When the pressure is very high, water will tend to gain its maximum density. And the maximum density of water is observed at which temperature? Are we aware? Yes. at 4 degrees. If you cool water beyond 4 degrees, there is a slight expansion as water tries to form the ice crystals. Basically, ice is an expanded form, an increased volume of water. So that is why water has a maximum temperature, maximum density at 4 degrees. This is one of the reasons. The second reason is that overlying pressure also tends to produce some amount of heat. And that heat also ends up maintaining the temperature at around 3 to 4 degrees Celsius at the bottom. Okay, so these are the two reasons. First reason, because of so much amount of pressure, water tends to remain in a state of maximum density. Its maximum density is 4 degrees Celsius. So imagine if the water would have cooled at the bottom to around 0 degrees Celsius, means formation of ice. So that would mean what? Water would need to expand. Now, would the above layers allow the water to expand? No. We are talking about 4 to 5 kilometers thickness of water above. That would never allow water to expand. Okay, so that is why, having said that, the planet has gone through phases where we know at least once when many of the oceans, many parts of the oceans got frozen right up till the floor. It has happened at least once. We know the evidence of it. The scientists basically they estimate that earlier also it would have happened. This is before the uh, development of all the modern species that you see. More than around 600 million years back, it is said that we went into a kind of a very cold winter where things started to freeze right up to the ocean bottom. But I hope this is now understood. Now, after that, we come to the portion of ocean salinity. Now, oceanic water, if ever you have been into the ocean, you have basically taken a bath or taken a swim in any of the coastal waters, you would have invariably have had the taste. It is very salty. Salt content is very high. So that measure of the salt content in the ocean water, that is what we refer to as ocean salinity. Okay, the measure of the salt content in the water, that is ocean salinity. Now, where does the ocean get its salt from? Where will it get its salt from? So let's suppose when we talk about the oceans, they are present near the land areas. So there can be consistent erosion, solution, dissolution of materials. Rocks might get dissolved, leading to the occurrence of salts. Fair enough. Then let's suppose a river is bringing the fresh water from a region. Now, as the river empties itself, even though in majority it will give the fresh water, it will also bring some amount of calcium sulfate that will be also deposited in the ocean. That will also add to the salt. Then, let's suppose underwater volcanic eruption. Underwater volcanic eruption at the region of the ridges. That will also add various different mineral particles, various different salt particles, potassium, magnesium, chlorides, etc. They are added. So multiple of these factors. Then you have the biological actions of the various species that will also keep on putting particles and salt content. So all these, they keep on adding salts to the oceans. That is why oceanic water is salty, it is saline. But over this long period of time, where for billions of years these oceans have been in existence, that would mean that the salt content would have gone up through the roof. But the salt content is almost consistent. Why? Despite these many sources of addition of salt, the salt content is still consistent in the oceans. That is because when we talk about the salts, Many of the times, many of these particles, they start combining together, reacting together, form larger particles or pieces, settle on the ground. Many of the times, you will observe, again, organic processes will consume many of these salts. Many of these salts get dissipated over a long period of time. Then let's suppose if you have a sea wave, if let's suppose recall the time that you have been to the coastline, coastal area, or if you have seen a coastal area in the movies and the images at least. Now, when these waves they hit the shore, if the shore is rocky, there is a lot of spray which is spread around. You would all have observed that when it hits the rocks, when the sea waves they hit the rocks, there's a lot of spray which moves around. Fair enough. That is the sea spray. That is what is known as sea spray. Even that sea spray will have the salt content, which is then carried by the winds. So, like that, you have sources which add the salts, you have sources, or you have various different portions or processes which basically remove that salt. Okay, now, how do you measure the salt content? So basically, you measure the salt content in any sample of water. So what do you do is, you take 1 kg of water. So basically, here let's suppose this is water. Okay. Now where will these salts be present? In between the water molecules? Wherever they get the available spacing between the water molecules, the salts will try to accommodate themselves there itself. Isn't it? So how do you measure it? So you take weight of salt per kg of water. So let's assume weight is 35, average which we take 35 grams per kg of water. So what it comes out to be? 35 grams per 1000 grams of water. So this is represented in 35 parts per 1000. Parts per 1000. And that is represented by the symbol like this. This symbol represents parts per 1000. On an average, at the global level, the salinity is maintained around 35 parts per 1000. Having said that, you have certain areas like Lake Van in Turkey, where the salinity level is 330 parts per 1000. You have the Dead Sea, where it is again close to around 250 parts per 1000. You have the Great Salt Lake, close to around 230 to 40 parts per 1000. Imagine 330 parts per 1000 means in 1 kg of water, you have 330 grams, one third of the salt content. Now, this salinity varies from one region to another. And it varies based upon latitudinal extent also, river water coming into a region also, Various factors that leads to variation. We will study about that. So first of all, what is oceanic salinity? So the total content of dissolved salts in seawater, that is known as salinity. It is calculated as the amount of salt dissolved in seawater of 1000 grams or 1 kg. It is expressed as parts per thousand or ppt. Seawater is primarily made up of many ions with chlorine, sodium, and sulfate. These are the ions which predominate. Okay? Now, here you can see various different sources which keep on adding salt and removing salt from the ocean water. Underwater volcanoes, on ground volcanoes, sea spray that removes the salt and various different ions, etc. Now, when we talk about the various different type of salts, salts don't only mean the salt that you consume, the common salt, even though that is the one which is present in majority. That is what gives that salty or saline taste when you consume that seawater. So NaCl is the most predominant, or the table salt that you consume, that is the most predominant of the salt types, right? Because of sodium ions, chlorine ions. Then you have magnesium chloride, magnesium sulfate, calcium sulfate. Ideally, for your prelims, you should have a clue of the first three prelims. Okay, so here you will observe basically that sodium chloride is present in maximum proportion amongst all the salts that are present in the seawater. Sodium chloride is present around 78%, magnesium chloride around 11%, magnesium sulfate around 4.7%, and so on. Overall, they have a close to around 35 parts per thousand representation of salinity. Now, this oceanic salinity varies from one region to another. And this variation in salinity will be very much a surface phenomena in itself. At the ocean bottom, it will be mostly consistent. It will only be a kind of a surface phenomena. So here, when you observe this oceanic salinity, variation of salinity. So let us approach this from a different angle. Rather than simply learning that precipitation will lead to what, evaporation will lead to what, let us approach it from a different angle. So here, let's suppose we consider a sample of seawater, 1 kg. These are the water molecules. Now the salts will be present in the spaces available, obviously. So let's assume here you have the salts which are present. Now, let's suppose this experiences rainfall or precipitation. Rainfall will add some amount of salt, but mostly rainfall will bring in fresh water along with it. Rainfall will always bring fresh water along with it into the oceans. So when you have this rainfall, you will have more supply of these water molecules in comparison, much more supply of these water molecules in comparison to the salt. And the salt will be present in little amount, earlier amount. Now, and listen to this carefully. As compared to the first scenario, proportion of salt after rainfall, proportion of salt in the amount of water. So, as compared to the first scenario, let's consider proportion of water in itself. Has proportion of water increased after rainfall, or is that ratio of salt and water going to remain the same even after rainfall? What do you think? Will the proportion of water and salt particles will remain the same, or will the amount of water increase? Will the proportion of salt decrease? What do you think will happen? It will increase, right? So here we can experience, we can basically conclude net addition of water molecules, water molecules. These will lead to what? Decrease in proportion of salts in comparison to water. Now you don't have that much salt, so decrease in salinity. Similarly, let us assume that you have a river, a flow of river in a region. Now that river water enters into an area, into the ocean. What will it lead to? River basically supplies fresh water. Some amount of sediments also the river will carry, but in bulk the river will lead to supply of more fresh water. So net addition of water molecules will be done by the river discharge. So rainfall, river discharge, melting of ice, groundwater moving into the region of the oceans, all of these, they lead to the net addition of freshwater molecules. So here, rainfall, river discharge, then melting of ice. Okay, meeting of the groundwater with the ocean. All of these will lead to net addition of the water molecules. So all of these events will lead to what? Reduction in salinity. So a region which receives higher amount of rainfall will tend to have lower salinity. A region which tends to receive lesser amount of rainfall will tend to have higher salinity. Again, I will repeat. A region which has got a higher amount of rainfall will experience a reduction or a decrease in salinity. A region which has got lower amount of rainfall, significantly lower amount of rainfall, there generally the salinity content will be high. Then let's suppose here you carry out a process such as evaporation. Now, when we talk about evaporation, basically, whenever you would have observed evaporation to be happening, let's suppose you have water dissolved and salt dissolved in water you have kept in a glass. You keep it outside. Now you allow the water to evaporate. Now at the end of it, when water evaporates, the salt will always be left behind. So while evaporation happens, only pure water evaporates. Only the water molecules, they get removed. The salt content gets left behind. So let's suppose evaporation happens. So evaporation happens means as compared to earlier, water molecules would be significantly reduced. In comparison, the salt would be left behind. So proportion of salt with respect to water will be higher now. Now, with respect to water, amount of water, you have higher amount of salt as compared to the earlier situation. So salinity has increased as a consequence of evaporation. What this has done is basically net removal of water molecules. So basically, this has led to comparative increase in proportion of salts. That has led to increase in salinity. Okay. Now, what are the factors which lead to this? So, for example, evaporation, will lead to an increase in salinity. Let's suppose then you have when you have freezing action, when you have, let's suppose, the seawater freezes to form icebergs, glaciers, etc. Now that will lead to what? That basically brings about the water molecules freezing up and much of the salt particles left behind. So in a region, let's suppose the top layer of water starts getting frozen. So most of the water molecules will get frozen. Some salt particles will also be captivated, but majority of the water molecules will be frozen. The remainder of the water, that will be left free. And there, in the remainder of water, all that salt will be left behind. So as compared to earlier, now the water has got more amount of salt which has been left behind. Right? So freezing action can also lead to an increase in salinity. So the regions where there is a greater amount of evaporation, salinity will be high. The region where there is a greater amount of rainfall, salinity will be low. So if you compare the equator with the tropics, the subtropical region, around, let's suppose, 30-degree north and 0-degree, which will have a higher salinity, 30-degree north or 0-degree? Which will have a higher salinity and why? Higher salinity. Ritika, correct. Sakshi, correct. 0-degree, I'm referring to equator here. I'm not referring to 0-degree at temperature. 0-degree, okay. Many of you think 0-degree, no. 30-degree north latitude or 0-degree equator? Okay. Aryan, Sakshi, Muskan, Megha, Sapna, Nikita, Shalja, Seema, Radhika, Abhishek. Lalita, Deepika, Charu, correct. Basically, at equator, you receive rainfall on a daily basis at the region of equator. You have convectional rainfall. So evaporation happens, but substantial amount of rainfall on a daily basis also happens. Some of the most rainiest areas across the world lies at equator. At around 20 to 30-degree north, we are witnessing the subtropical high pressure belt. The presence of subtropical high pressure belt means a complete lack of rain in that area. But will there be an evaporation in existence? Yes. Temperature is still high at 30 degrees. So there might not be rainfall or cloud formation, but evaporation will happen. So evaporation increases the salinity, lack of rainfall. So salinity is always going to be higher at the tropics. In fact, across the globe, the most saline waters across the globe are to be found in the region of the tropics. All this Dead Sea, Lake Van, Great Salt Lake, all these of high salinity you will observe in tropics. Okay? Now, then, so surface water salinity depends on factors such as evaporation. More evaporation means greater amount of salinity. Precipitation or rainfall. Less precipitation means more salinity. More precipitation or more rainfall means less salinity. Fresh flow of river water. Wherever the rivers come through, there the rivers will basically provide that fresh water along with salt, the sediments, but more water is supplied. Freezing and thawing of glacier. Freezing reduces salinity, and thawing basically is the process of melting of glaciers. Melting increases salinity. Okay? Or rather, it is the opposite. Decreases the salinity, and freezing will increase the salinity level. Why? Because thawing or melting of glacier means fresh water is added, and freezing means lot of water is consumed in the formation of the ice. Salt is left behind, so that salt increases the salinity of the remaining water. This is a chart which you can basically utilize to revise this. So decrease in salinity wherever you have net addition of water molecules. Net addition of water molecules. And wherever you have net reduction of water molecules. So you can see rainfall will reduce salinity, river runoff will reduce salinity, groundwater flow to ocean will reduce salinity, melting of ice will reduce salinity, evaporation will increase salinity, and freezing of seawater will also increase salinity levels. So this is the latitudinal variation in terms of evaporation and precipitation. So basically you observe at the region of equator, the rainfall is very high. The amount of rainfall is very high. So when the amount of rainfall is very high, that means salinity at the equator is comparatively lower. Compared to where? Compared to the tropics. Because in tropics, you will observe the evaporation rate is very high. Rainfall is very low in the tropics because of the presence of the subtropical high pressure belt. So that is why the salinity is highest in the region of tropics. Of the tropics. Okay. Salinity is the highest in the region of the tropics. And basically, you will observe that in general, salinity levels reduce, show a reduction as one moves from equator to the poles. Okay, so as one moves from the region of the equator to the region of the poles, there is a general decline in salinity levels. There is a discrepancy at tropics where still the evaporation is so very high, lack of rainfall, so there is the maximum amount of salinity observed at the tropics. But in general, the trend that you will observe is the declining trend from equator to the region of the poles. Okay, why? Why it is going to decline from equator to the poles? Because in polar region you have basically no amount of precipitation, almost no amount of precipitation at all. Then, for example, in the region of the Arctic, you still have in the region of the Arctic, the movement of warm waters will cause some evaporation there, right? So evaporation will always be there, but there will be very less precipitation. So in general, the salinity levels will also be altered by freezing and melting of ice there. So that is why you have a variation. But please reframe your question. Do Caspian and Aral Sea have the same salinity compared to the oceans? No. For example, when you talk about the region of the Caspian is going to receive large rivers such as River Volga. River Volga drains into the region of the Caspian. So the northern portion of the Caspian Sea, where River Volga drains, there you will have such abundant supply of fresh water that it will indicate a low salinity level. By the time that you come to the southern part of the Caspian, around the region of the Gulf of Karabakh, there you will observe that there is no supply of fresh water, only evaporation is predominant. So Caspian shows that variation where the northern Caspian is less saline, southern part of the Caspian is significantly more saline. Why freezing increases salinity? Because see, when you have freezing, so let's suppose you have the water. Let's suppose you have the water. Now, some portion of that water got frozen into sea ice. Let's suppose it has got frozen into sea ice. Now, majorly, this will consist of what? Sea ice. Majorly, ice will consist of water molecules always. Right? Some amount of salt, but majorly water. Now, from the earlier comparison of this sea water, can we say that there has been removal of water? Because water has been converted into ice. So, that means because there is removal of water, now per water molecule, there is going to be a greater proportion of salt in the ocean, increase in salinity. Okay. And then please address this question. What could be the reason of salinity of land water in some places, but normal at other places? Evaporation. Evaporation is one of the significant factors, supply of river water as well. For example, take a look at Sambar Lake. Sambar Lake has got no supply of fresh water, but significant and very large amount of evaporation. So evaporation will always take away the water molecules, leave behind the salt molecules. So Sambar Lake is saline. Whereas consider a pond near your village, in your town. Most of the ponds most probably are basically refurbished or resupplied by the groundwater or the rainwater. They are fresh water. So that is why some portions of the inland lakes or certain inland lakes you will find to be saline, certain inland lakes you will find to have the fresh water. And where is more salinity? Equator or at poles? Equator. In equatorial region, rainfall is high. In polar region, freezing is high. So salinity should be more in poles. In comparison to the polar area, equatorial region experiences much higher rate of evaporation. Much higher rate of evaporation is experienced in the equatorial areas. Polar areas, the evaporation is almost negligible, right? So in many of the polar areas, there's a seasonal variation of salinity from 0 to 35 parts or 41 parts per thousand. Whenever there is freezing, salinity tends to increase. Whenever there is melting, salinity comes to absolute zero. So there is that variation which does happen. Okay. So here, if I show you these salinity levels, observe here. This is the variation in. So Ankush, your detailed question is, in equatorial, rainfall is high. In polar region, freezing is high. Okay, so the same salinity. Same question. I hope that is understood. Because, see, understand, observe this. Observe where the evaporation levels and precipitation levels are at the region of the Arctic. Almost negligible, right? Almost negligible. Whenever there will be melting, there will be high salinity, low salinity. Whenever there is freezing, always salinity will tend to increase. So there is a seasonal variation also. Ashish, I am, sir, I am Ghaziabad. I find it very difficult to believe. You might be living in Ghaziabad. So I am Ghaziabad, but here the groundwater we use is highly saline. Yes, it is. How evaporation will take place in water below the ground. See, when you say that the groundwater is saline, as is the case with almost the entirety of the northern plains, from the region of Punjab, Haryana, UP, Delhi, nowadays even northern Rajasthan, the central portion of Delhi. Now, there, the presence of minerals, the presence of salt content in the groundwater is very different from this entire concept of salinity. There, the groundwater is contaminated. It is not saline, it is contaminated. Contaminated with cadmium, nitrate, fluoride, arsenic, and in the regions of Punjab, even uranium, lead, zinc. For example, around the region of Western UP and the region around Delhi, the groundwater is so very contaminated with fluoride and arsenic. People tend to suffer from issues of the bones, fluorosis, right? Many of us are not even aware. Then black foot disease because of arsenic. So why does that contamination happen? Is because of over extraction of groundwater from the underground beds. So basically what happens, if I hope you can imagine that in the underground level, when you extract that groundwater, water is basically present within the permeable system of the rocks. Now you extract that, keep on extracting that, water level reduces. Okay. So recall that if ever you have basically seen a tank of water stored or a well, or let's suppose even an earthen pot in which you have stored water or drank water from it during the summer. As long as you drink water from the topmost portion, it is very clear, very pure. By the time that you reach the bottom portion, you start getting some sediments, some portions of that pot also, some of the impurities also you get. I hope everybody can relate to that experience sometime or the other in your life. That is why everybody lines up to have the first supply from the well or from the tank or from even the earthen pot. Because the one who drinks at the last will get a lot of sand particles, mud particles. That is the same phenomena which is happening in the region of particularly the central West UP, mostly the West UP, Haryana, Punjab, northern Rajasthan. Due to over extraction of groundwater, the groundwater has become contaminated. It is not salinity, it is pure contamination. Okay, I hope that is understood now. Charu, at 0 degree latitude, why there is low salinity whereas evaporation must occur more near equator as compared to tropics? Charu, understand, at equator evaporation occurs but not as high as the tropics. Why? Because absolutely highest temperature is always observed in the region of the tropics. Why? Because the tropics are a region of the subtropical high pressure belt. And because these are the regions of the subtropical high pressure belt means an absolute lack of rainfall, an absolute lack of cloud formation. Right. So in the case of the equator, you still have cloud formation, which will cool down the surface sometime during the day or during the evening, reducing the rate of evaporation. At least when it is raining, that much evaporation will not happen. But in the tropics, no rainfall, only evaporation. Temperature goes very high, more evaporation, hence a higher level of salinity. Okay. Yes, Mehta. So this is where we take a break, digest this, then we move to the horizontal distribution of salinity, waves, tides. The thermohaline circulation is something we'll discuss first, waves, tides, and then the ocean circulation. Okay. So let's take a break for 15 minutes. Let's be back. A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm. Thank you. So, on Saturday, I will announce it once again at the end of the session. But on Saturday, that is day after tomorrow, we'll have an extra session from around the same time. That is 7:30 to roughly around 11:30 is when we will have that session. So Saturday morning, we will have the session from around 7:30 a.m. up till around 11:30. That is going to be the extra session. Okay. Rani, is narrowness of the Bay of Bengal the only reason for more cyclones? We have talked about multiple various reasons till now, haven't we? Even the air circulation, even the case of when we talk about, let's suppose, the movement of during the negative Indian Ocean dipole, the neutral condition of Indian Ocean dipole, the normal case of the Walker circulation, all of these, we have talked about that, how they favor occurrence of more cyclones in Bay of Bengal, right? So there are multiple factors. One more factor we will study here. There is one more factor which is associated, that is the movement of the winds. So here in the region of Bay of Bengal, due to the movement of trade winds, you will experience downwelling in action in this area. Same is the case with the South China Sea. Same is the case with the region of Gulf of Mexico also. So all of these also end up raising the temperature of that area. So that is also one of the reasons, but another reason we will study in very short duration. Now, then we come to the portion of here, the horizontal distribution of salinity. How is it that salinity tends to vary from one region to another? So basically, the salinity for normal open ocean on an average is around between 33 to 35, 37 parts per thousand. On an average, it can be taken to be 35 parts per thousand is the salinity level on an average. Okay. And also understand that whatever variations in salinity that you observe due to precipitation, due to evaporation, due to freezing, due to melting, all that variation in salinity is observed only at the surface level. At the deeper level, at the lower level, the salinity is almost consistent to be around 35 parts per thousand. So let me write it down here also. So all these factors influence salinity at the surface up to the depth of few hundred meters. A depth of few hundred meters. Salinity at the bottom is consistent. Okay. Now here, after this, when we talk about the horizontal distribution of salinity, so there are multiple factors. Influx of river water in certain areas, that reduces the salinity, that immediately will lower the salinity. The movement of ocean currents in certain areas. For example, let's suppose we talk about the ocean currents such as the North Atlantic drift. That North Atlantic drift would raise the temperature in the Northern Atlantic. Raising the temperature would mean greater amount of evaporation. Greater amount of evaporation would mean increase in salinity. So these factors does influence the salinity. In landlocked areas such as Red Sea, in landlocked areas such as Mediterranean Sea, the rate of evaporation is very high. precipitation is not that high, so salinity levels are high. So the salinity can be as high as 41 parts per thousand. While in estuaries, the deltas of the Arctic, basically you will observe that there's a seasonal variation from 0 to 35, particularly due to the melting and freezing. Due to melting and freezing. Whenever there will be melting, salinity would reduce to close to around 0. Large amount of ice melt, salinity would reduce. Large amount of freezing action again would lead to an increase in salinity. So here by this image, observe the variation in salinity as per the color pattern. You will observe salinity is very, very high in certain areas. For example, here, observe in the region of Mediterranean. Observe in the region of Red Sea. Why? Because it is so very closely surrounded by land masses that the heating of the land masses will heat up the water body, will lead to increased amount of evaporation. Very little amount of precipitation in these areas, high salinity levels. Now the salinity levels at the tropics, observe the tropics. Salinity levels are generally very high. Now, as you move further northwards, Arctic, by the way, Arctic and Antarctic, should they represent same conditions of salinity? Should they represent different conditions of salinity? Why? Yes or no? And if yes, why? If no, why? Arctic and Antarctic, should they represent similar conditions of salinity or should they represent different conditions of salinity? Very good. It will be different. Very different. Why? First of all, Antarctica is a continent surrounded by water body. Arctic is a water body surrounded by land masses. So there will be different amount of heating and cooling. Okay. So the frequency of melting and freezing exercises or the occurrence of melting and freezing in the region of the Arctic will be much more common, which will be much more predominant. So that freezing and melting will be more predominant in the region of the Arctic. In the region of Antarctica, it is the continent which is frozen. Water is not frozen to that much, right? So it is the continent which is frozen. So that is why around Antarctica, salinity values will still have some consistency. Around Arctic, the salinity values will change. Around the region of Arctic, you will also observe that because of this melting activity, lower salinity is observed. Here, observe the North Atlantic drift carries warm water to the higher latitudes. These warm waters Atlantic drift carries warmer waters to higher latitudes. Warmer waters being carried to the higher latitudes means increase in evaporation. Excuse me. Observe the equatorial areas. Very heavy amount of rainfall. Low salinity levels. Observe the region of Bay of Bengal. Compare it with the region of Arabian Sea. Bay of Bengal has got very low salinity level as compared to the region of Arabian Sea. Why? Why is it that Bay of Bengal, even though closely surrounded by land, much smaller water body as the Arabian Sea, has got very low salinity levels as compared to Arabian Sea? Good. Because of significant amount of flow of river water. in the region of Bay of Bengal, in the region of Arabian Sea, first of all, if you consider the major rivers, Indus, Narmada, Tapi, these are the major rivers. Tapi is also not that major a river. But if you consider the region of Bay of Bengal, Irrawaddy, Brahmaputra, Ganga, along with the portion of Yamuna, Mahanadi, Krishna, Kaveri, Godavari, all these major rivers, they drain into the region of Arabian Sea. Similarly, observe here, even in the case of the Andaman Sea, even in the case of the region of Gulf of Thailand, even in the area of South China Sea, where you have the movement of rivers such as Mekong, Yangtze, etc., all of them, they have lowered the salinity levels here. Okay, so influx of river water lowers the salinity here. Observe, salinity level is low. Why? Which particular reason can be attributed for the low salinity levels in this area to the west of Africa? Which particular river? Let me know if you can think about the river which can lower the salinity in the region of west of Africa. Nile does not drain into that area, my dear friend. Nile, I had given you the map pointing for Nile, so clearly nobody has done that. Volga. Volta. Okay, I had given you the map pointing for the various rivers. How many of you did honestly do that? Clearly, none of the ones who have been answering. Now I have few people searching on the Google, coming back with the correct answer. How many of you did do the map pointing that I gave? Okay. Ask anything more. Will you give the same thing to UPSC? That this question I don't know. Frame another question for me. I have read this portion carefully. That is not the excuse which floats well with the UPSC. Observe the river Congo. Observe river Congo. The lower portion is around Zambezi, but observe river Congo. Congo drains from this area. Nile drains through this region, my dear friend. All those who significantly jump towards Nile, Nile drains through this area. I had told you to mark out white Nile, blue Nile also, but Niger drains through this area. Volta also drains here. Okay, so basically, okay, coming back to it, there is no point repenting on the past. Coming back to it, when we talk about the influx of river water has got the potential to lower the salinity levels significantly. Now, this does have a substantial amount of influence. We'll take a look into that. In hot and dry regions where evaporation is high, the salinity sometimes reaches up till around 70 parts per thousand. Maximum salinity in the world is observed between 20 to 30-degree north latitudes. It is the region of the tropics. And that too in the northern tropics, not the southern tropics. Why? Because the tropics of the north is more dominated by the land masses, so the influence of heating will be very high. Whenever the influence of heating is higher, there will be greater rate of evaporation observed. So that is why here tropics, faster rate or a higher rate of evaporation. Evaporation. Okay, almost negligible rainfall, very high amount of evaporation. North Sea, for example, being in higher latitude. Where is North Sea? In which part of Europe? Okay. Near UK, correct. near the region of UK, northwestern part of Europe. That is where North Sea is. So clearly map pointing has been done by a very few people. So North Sea being in higher latitude still records a higher salinity due to more saline waters brought by the North Atlantic drift and due to the influence of the ocean currents that can also end up impacting salinity levels. So here we know which one has got more salinity. It is always going to be Arabian Sea, which has got more salinity. Now, let us form a linkage between the property of water experienced in the region of Arabian Sea and Bay of Bengal. But before that, salinity is what? In nutshell, salt content, the amount of salt content which is present, that is salinity. So, if I have two different samples of water, by the way, are we aware about what is density? Density is mass per unit volume. Density is mass per volume. Okay. Let's suppose we have the same volume of water. In one, you have the salinity of 43 parts per thousand. In the other one, let's suppose the salinity is 20 parts per thousand. This is A, this is B. Which is going to be heavier and denser out of A and B? Which is going to be heavier and denser? Good. Very good. A is going to be heavier. So that brings us to a conclusion. More saline waters, or rather, salinity density is proportional to salinity. So what does that mean? And listen to this explanation, this particular next 5 minutes very carefully, not to be found in the books. So salinity is proportional to density, means higher salinity means greater density. And also, I won't be wrong if I say that the water will be heavier. More saline water will be slightly heavier. Lesser salinity will mean less density, basically means lighter waters. Fair enough. So that will bring me to my second conclusion. If let's suppose we talk about the region of Bay of Bengal. Now Bay of Bengal, as we speak every minute, for a brief moment, just imagine that you are having an overview of Bay of Bengal during this time. At around 7:15 p.m., you are taking a look at the region of Bay of Bengal. You will have every minute endless amount of water being brought by major rivers, Brahmaputra, Ganga, Brak, Iravadi, Mahanadi, Brahmani, Godavari, Krishna, Kaveri. All these rivers are bringing water into Bay of Bengal as we speak. Now these waters, they are basically going to be fresh water. Rivers bring fresh water, low in salinity level. Now, low salinity level water or fresh water, can I say, as per my earlier conclusion, that low salinity level water is going to be lighter? Lighter water will tend to float. denser water will tend to sink. Fair enough. So, when the rivers are bringing in this fresh water, that fresh water will tend to float for some time. Maybe after 1 month, 2 months, or 3 months, maybe due to evaporation, that water becomes saline and more fresh water comes in. So, the earlier water starts sinking down. But as this fresh water is supplied, can we all agree to this basic fact that the fresh water is going to be lighter because of low salt content? It is going to float on top. Any problem up till this point? Very good. So let me write it down. Large amount of fresh water stays. Or simply put, let's have a generalized statement from which you can derive this on your own. When water of different salinity levels are present, less saline waters stay on top and more saline waters sink to the bottom. Maybe after, as I said, maybe after a month, even that fresh water which was provided into the Bay of Bengal after a month of evaporation, let's suppose that becomes also saline. But by that time, the rivers would have brought in huge amount of more fresh water. So always we will be observing that churn where the oceanic waters arrange themselves in various different layers based upon density. Lighter water will always tend to float on top, denser water will always tend to move to the bottom. Fair enough. This arrangement of oceanic water in terms of various layers based upon the density, based upon the mass, that is what is also referred to as ocean stratification. So, water in the oceans arrange themselves in layers based upon density. That is ocean stratification. I hope till this point of time it is clear. So, as compared to Arabian Sea, and when you compare Arabian Sea and Bay of Bengal, where will you observe this frequent occurrence of stratification? In Bay of Bengal or in Arabian Sea? Where will you find the frequent formation of these layers? Always in the case of Bay of Bengal. Why? Because Arabian Sea does not have that much influx of rivers. But in the case of Bay of Bengal, so many freshwater rivers bring it that huge amount of fresh water that there will always be that layered formation, isn't it? So ocean stratification more prominent in Bay of Bengal as compared to Arabian Sea. I hope everybody agrees with this conclusion. More prominent in Bay of Bengal as compared to Arabian Sea. Okay, now what is the impact of it? Why should we worry if there is ocean stratification or not? There is an impact. Let me tell you how. So, the lighter waters in Bay of Bengal tend to remain on top. Then you have the denser waters. Arabian Sea, on the other hand, will represent a much uniform presence of water, where you will have the denser, more saline water to be present. Okay, this is Arabian Sea. This is Bay of Bengal. Now, when the solar insolation falls, let's suppose this is the sun, the solar insolation falls, the solar insolation falls. Now, in the region of Arabian Sea, this solar insolation will get distributed almost uniformly through the depth. So the heat will be transmitted, right? Whereas in this region, you have areas of different density. So can we say significant heat will be concentrated here? Some heat might percolate in the lower portions also. But because the densities are different, there will be substantial amount of heat concentrated here. Isn't it? Here you have the water of different densities. In Arabian Sea, you have the water of uniform densities. So, where is it that the sea surface temperature will be higher and will reach a higher level much earlier? Where is it that the sea surface will get heated more quickly and more significantly? Arabian Sea or Bay of Bengal? Very good. Bay of Bengal, because that heat is concentrated in the region to the top, whereas in the case of Arabian Sea, that heat gets distributed uniformly almost. So the sea surface temperature rises very quickly and very intensely over the region of Bay of Bengal. Temperature rises very quickly and frequently. When that sea surface temperature significantly goes up, which atmospheric phenomena will be observed over these areas? Let me know. A tropical cyclone. So, under these conditions, out of Arabian Sea and Bay of Bengal, which is going to observe more frequent cyclones is going to be Bay of Bengal. And a major role to be played is by ocean stratification. Excuse me. So, ocean stratification plays a major role in that. This is one of the reasons why you have a lot of such tropical cyclones getting formed even in the region of South China Sea. Because there also you have ocean stratification. Because of large rivers such as Yangtze, in the nearby vicinity you have Mekong, etc., bringing in huge amount of waters, fresh water. In the Gulf of Mexico also, while that onshore winds will lead to downwelling, rise in sea surface temperature, but movement of rivers such as large river in the region of Gulf of Mexico, which is a large river which drains, one of the large rivers that drains in the Gulf of Mexico. I've given you the map pointing about it. Mississippi. Mississippi is, along with the various other smaller ones, they also bring a lot of fresh water, attaining that ocean stratification. So it is because of that stratification of the oceans that the temperature increases. Okay? I hope that is understood. So this is one of the main reasons, one of the other main reasons why cyclones frequent the region of Bay of Bengal as compared to the region of Arabian Sea. Okay? Now, can we say that density? Yes, Muskan. Vikalp, why does heat concentrate itself in low saline water? Is there a law? What law will be there? It is heat does not know low saline or high saline. Heat knows, any energy form knows about density. You would have seen light, how it travels, sound, how it travels. When any form of energy travels through materials of different densities, it tends to experience refraction, internal refraction, and so on. So that is why there will be that heat which will pass on to the lower layers. Some of that will be re-reflected back closer to the sea surface. So that consistent trapping of heat in material of one density will bring about the condition where the surface temperature raises up very quickly. And the deltas which drain out in the sea, can they even carry the higher temperature of the landmass and make the Bay of Bengal warm? It is not only the deltas. Basically, as I told you, when you have the landmass which gets warmer, by the process of conduction, water body, when is in contact with such hot landmass, will automatically start experiencing a higher temperature. And Bay of Bengal is enclosed, much smaller a water body, much closely surrounded by landmass. That is another reason why Bay of Bengal experiences such higher temperature. Okay. Air passes Bay of Bengal heavier than Arabian Sea. What? Air passes Bay of Bengal heavier than. See, I'm not able to understand the question. Air passes over Bay of Bengal heavier than. Still not able to understand. See, if you're talking about air movement or movement of winds will be determined by the low pressure of over the land. They will not be determined by the stratification unless and until you have creation of low pressure. Difference in density in Bay of Bengal leads to, yes, Prem Kumar, that is correct. All rivers have less salinity unless and until you are talking about an inland river, kind of an ephemeral river like Luni. So there is a variation in salinity from the upper course to the lower course. We'll come to that in the portion of the next few modules. Now, the vertical distribution of salinity. As I have consistently told you, that all these various factors, they will tend to influence the salinity on the surface. At the lower level, salinity tends to remain consistent. At the lower region, salinity tends to remain consistent. It is only at the surface where that salinity tends to vary. So salinity changes with depth, but not same on all locations. Okay. So salinity at depth is very much fixed around 35 parts per thousand. Okay. Now that means whatever is the surface variation, whatever might be the variation of salinity at the surface, at various latitudes, at various regions, at the bottom, the salinity is largely consistent around 35 parts per thousand. So here, if you observe this, okay, let's suppose you observe this. So here, observe at equator is the salinity is around 35 parts per thousand. At the bottom, it will reduce to maintain to be around 35. In the region of the tropics, where salinity is close to around 37, as you go to the bottom, salinity tends to remain consistent. In the higher latitude, you might have a very low salinity at the surface due to other activities, melting, etc. At the bottom, it is consistent. So, at various different latitudes, you will come across that zone of transition. That zone of transition, there is going to be a zone of transition. Zone of transition where salinity indicates a variation from the surface level to the bottom. Right? So that zone of transition is known as halocline. Just like thermocline represented the zone of transition where the temperature changed, here there's a zone of transition where the salinity levels will indicate that sudden change. Bhima, evaporation is more in Bay of Bengal means more salinity. So evaporation is one of the factors. I hope you were in the session when we looked at the map. Were you in the session when we looked at this map, Bhima? Observe here, the salinity levels in Bay of Bengal are very low. And that is attributed to the huge amount of river water, influx of river water, such as Iravadi, Parak, Brahmaputra, Ganga, Yamuna, Mahanadi, Krishna, Godavari, Kaveri, Pinar, all of them. They continue to drain in their fresh water. Observe here also, River Congo provides that fresh water. So here also, it will be less saline, right? Wherever Amazon will make the water less saline. So wherever you have large influx of river water, South China Sea, Gulf of Thailand, in every of these areas, large influx of river water will basically mean what? That fresh water becomes prevalent, availability of fresh water is there, salinity levels will go down. Okay, I hope that is understood, Bhima. So higher salinity is much more denser, stays below the water having lower salinity. Higher the density, water goes to the deeper extent. This property leads to ocean stratification or arrangement of water into layers. Stratification is basically arrangement into layers, right? Stratification is derived from the term strata, which means layers themselves. So this is arrangement into layers. Into layers. So that is why, remember, I had asked you when we were discussing the mains PYQ about why more tropical cyclones occur in the region of South China Sea, Gulf of Mexico, and the region of Bay of Bengal. Now, majority of the candidates, they will give certain type, by majority, 99.9% of the candidates will give this simple logic that everybody will give, that these are smaller water bodies surrounded by land, get heated up, they experience the onshore trade wind, so there will be downwelling leading to a rise in temperature. This is where, as a candidate, if you are able to diversify your points, include the factors such as that during the Enzo circulation, South China Walker circulation, normal Walker circulation, South China Sea, and the region of Bay of Bengal are more prone to tropical cyclones as compared to Arabian Sea. During the negative and the neutral phase of IOD, both the South China Sea and Bay of Bengal experience that low pressure. Then add closely surrounded by landmass, etc. Then add this completely different point from different module, that is oceanography, about ocean stratification, downwelling, ocean strat. When you bring forward these points, that creates a very good impression in the mind of the evaluator. And trust me, the impression that you create in one of these questions can have a repetition or a follow cascading effect on the other answers also. Generally, when the evaluator comes across an answer copy where the content is covered, plus there is some additional and a diverse point of view which the rest of the crowd has not written, that impression is created that this candidate is different, this candidate knows how to interrelate. So in the next questions also, maybe you have written an average answer, you will get 1 marks more than your competition. So think about it, create such answers easily. Every GS paper, you might end up creating a difference of around 20 marks, 20 to 25 marks. This might not seem very high as of now, that in 250 marks, what you are saying of 25 marks, it is very huge. Let's assume even 20 marks. So, 4 GS papers, if you follow the same ideology, the same approach, the same mentality, you are creating a difference of 100 marks only in your GS. So even if, let's suppose, in your optional you have performed very average, you have scored 270, your competition has taken one of those subjects where they have got very good marks. Let's suppose they have got 330, you will still be at an advantage over them. 100 marks of a difference in GS paper over average, that is almost sure to put you in the merit list, unless and until you completely do it out in the interview where you basically bring forward that side of yourself which you also don't like. Then basically interview is a kind of a bonanza or a kind of a surprise. Other than that, you will definitely find your way in the merit list if the interview is average. So that is why please pay attention on where you can create that difference, which will be different from the rest of the answers. Okay. Bay of Bengal itself a river except the falling river? Please elaborate this statement. One of the most interesting statements I've come across in a long time. Bay of Bengal is a river? Who told you Bay of Bengal is a river? Bay of Bengal is not a river, my dear friend. Please open up the atlas, look at the map of the country at least, look at the portions to the east and the west. Or if you are asking something else, your language is basically betraying you here. So the water of highest salinity across the world, you have Lake Van in Turkey with a salinity level of 330 parts per thousand, Dead Sea with a salinity level of 238 parts per thousand, Great Salt Lake with a salinity level of 220 parts per thousand. That is the salinity levels in the various water bodies. Highest water body, Lake Van. Why? This is I had told you to map this out also, but I'm sure many of you have not done. Observe the region of Lake Van. It is surrounded by land. It is a small water body surrounded by land from all sides in the tropics. So there is very high rate of evaporation, almost negligible rainfall. Now, after this, we come to the differences in water density basically affect the vertical mobility in terms of oceans. So here, let us look at the density of ocean. Ocean water. Now, when we talk about the density, basically it is how closely the materials are packed together. So, water with high salinity, again, a conceptual portion, so pay attention. Water with high salinity means high salt content is denser than water with low salinity, something that we have already seen. Low salinity water is lighter, so it tends to float. High salinity water is denser, heavier, tends to sink. Cold water is denser as compared to warm water. So, warmer water means low density. It will come to the top. Colder waters will sink, right? So, warm water, low density. Cold water, high density. Also, high salinity, salinity means high density. Now, let us consider a typical situation of tropics in the northern hemisphere. Now, first of all, tell me, temperature in the tropics, will it be of the water? Temperature of water in the tropics, will it be high? Will it be low? And please follow this carefully. Temperature of water in the tropics, will it be high? Will it be low? Very good. Temperature will be very high because tropics are the heated areas. So, temperature is high. Salinity level in the tropics is high or is it low? In the tropics, we have seen it is amongst the highest. Now, here comes the conundrum. If the temperature is high, warm water, it should have low density. So, if the temperature condition is to be followed, water in the tropics should have low density. But if the salinity condition is to be followed, high salinity means high density. So if the salinity condition is to be followed, water has to be dense. If the temperature condition has to be followed, water will be less dense. What will be the end result? Will the water in the tropics be denser? Will the water of the tropics will be less dense? So whenever you have both temperature and salinity factors, both are at play, always remember temperature factor will predominate. I will repeat. Whenever temperature and salinity conditions both are at play, density will be determined by the temperature conditions. Why? Very simple. Let's assume you have water of low salinity levels. And let's assume water of very high salinity levels. Now, if I heat this up, regardless of whatever the salinity levels are, it will expand, particles will move away, density will reduce, right? So heating of the particles leads to expansion, which will reduce the density always. So I will write it down. So basically, whenever both salinity and temperature conditions are predominant, density will be determined by temperature. That is, okay. Always remember this. Now, here, more denser water tends to sink, less dense water tends to rise up. In the lower latitudes around equator and the tropics, there is so much amount of heating that the top surface tends to expand. There is that expansion of water. As that moves, again, the bottom portion which comes up, that will also tend to expand. So here, let us take a look at the circulation induced because of that. That is what is known as thermohaline circulation. Circulations. Excuse me. Now here, let us consider water at different latitudes. So let us consider the lower latitudes first of all. And also the region of the higher latitudes. Now, let's assume this is the bottom. These are your lower latitudes. Closer to equator, higher latitudes. So in the lower latitudes, what you actually experience is the fact that due to higher amount of insolation, temperature increases quite significantly. And that consistent amount of heating leads to the ever slight expansion of water. So here, higher amount of solar insolation basically leads to higher solar insolation leads to expansion of water. Now, water in these lower latitudes, they gain a height advantage or a height difference of around 8 to 10 centimeter. Now, that is huge. A height difference of 8 to 10 centimeter from one latitude to another can immediately induce a movement of water. So that is why there will always be a height difference between the lower latitude and the higher latitude. Induces a difference in height in between lower and higher latitude. So because of this, there is a movement of water which is initiated. That movement of water is initiated from the lower latitude to the higher latitude. Till this point, is there any doubt? Is this understood? That there will be such movement of water from the lower latitude to the higher latitude. It is understood? Okay. Now, what happens when water reaches the higher latitude? As soon as water reaches the higher latitudes, there are a couple of things which will happen. First of all, first thing that will happen is that in the higher latitude, temperature will be very low, isn't it? So, in higher latitudes, temperature is very low. Temperature is very low. What will it lead to in terms of its density? Cold temperature leads to higher density. Then, in the higher latitudes, freezing will be observed. Will occur. Now, freezing, what will it lead to? Salinity. Freezing, more salinity. Very good. So, salinity will increase. Salinity will increase. As a result of that increase in salinity, can we say that density of water will increase? So here, both as per the temperature and salinity conditions, by the time the water reaches the higher latitude, its density would have increased quite significantly. Fair enough? Now, when the density increases so significantly, what will happen? Can we say that the water will start to sink? Right? Can we say that the water will sink? So here, water starts to sink. Water sinks due to increase in density. Meanwhile, in the lower latitude, the surface water had moved away. So what would have happened? Water from the lower levels would have risen up. They would also have moved away after heating and expanding. Then what would have happened? Water from the surrounding areas would have been driven up. They would have also moved away due to heating. So there is always a vacancy here created because water is consistently getting heated up and passed away. So here, this water, which is sinking here, will go to fulfill that vacancy. So you have a complete circulation which is induced in the ocean between the lower and the higher latitude. But this circulation which is induced, this circulation which is observed why? Because of basic differences in temperature and salinity conditions. That is the only reason. If the temperature and salinity conditions would not have varied, this circulation would not have happened. It is the temperature conditions in the lower latitude which has led to the expansion of water. Increase in salinity in the higher latitude has led to the sinking of water. So the factor of temperature and salinity has induced this circulation, hence thermohaline circulation. This allows for distribution of heat across the entirety of the world's oceans. where the lower latitudes receive surplus amount of heat. The higher latitudes, they are heat deficient. So that is why there is that circulation which transfers that heat from the lower latitude to the higher latitude. Along with that, it also helps in transfer of the nutrients from one part of the ocean to the other. And that consistent transfer of nutrients is very, very helpful, significantly beneficial for a host of various marine species. Okay, so that is the reason of this thermohaline circulation. Now, so we have seen till now multiple times that you have denser water tends to sink while relatively lighter water tends to float. So that is why warm water from the lower latitudes, they are brought over to the higher latitudes, they tend to sink and then they move back. Okay. Now we come to the motion or the movement of observed in the oceans. So you have different types of movements. So out of these movements in ocean water, thermohaline circulation is also a movement, by the way. So movement in ocean water, this is going to be very relevant for your mains examination, along with the current affairs perspective that we study about the Atlantic meridional overturning circulation at the later point of this module. Tides are going to be important for your prelims, and ocean currents are going to be important both for your prelims as well as for your mains. Waves are not that important. But first of all, we will study waves, because when you stare at these oceans, you observe these features, this kind of a movement of water. First of all, is this a tide or is it a wave that is indicated in the image here? Is it a tide or is it a wave? Very good. For every person who says wave, there is another person who says tide. For every person who says tide, there are two people who say waves. So basically, a full on confusion and no clarity. And that is because from our childhood days, somebody tells us this is a wave, stay away from water, it is wave. Somebody tells you that you see tides. Tides are something which happen in the coastal areas. Look at the tides, they are so very dangerous. Tides can basically carry you to the water. So from our childhood days, we have been born and brought up, and we have grown up looking at these as something which is more or less similar. This image that you see, and we have the smarter ones, we have, it is a tidal wave. Hmm. Tidal wave is a very different thing. Okay, this is basically a wave that is present. So these events that you see in the sea, that is a wave. Okay, so what is a wave? So it is a very simple phenomena. Seawater, if you observe the seawater rise in water level is shown here. Where is the rise in water level? It is like, okay, you are correct. Whatever is the answer that you have given, tide or wave, that is correct, or tidal wave, whatever is the answer that you have given is correct. Now listen to the concepts. Okay, such ego with the answers if you have. What do you do in the test series when you find your answer is wrong? How many of us have the tendency to blame the answer paper and the explanations that they might be wrong? I am correct. When I say Article 52 refers to this, who are they to say it refers to president? So never have that tendency. At least till you clear the exam. After the exam, you write your own book. So basically, let's suppose we consider the sea surface. Now on the sea surface, from some region to another, consistently there will be movement of winds. Consistently. Winds will be blowing. The winds will try to tide is an extreme form of waves. Okay, fair enough. Understood. You all know what is tide. You all know what is a wave. Now let us concentrate on waves. I'll talk about tides also. So, when the winds blow over the surface, they will have their own frictional drag. When the winds blow over the land areas, you would have seen that they tend to pick up small particles, small, if the wind is strong enough, small paper pieces, etc., they can lift out to a greater height. So a similar phenomena will be observed here also. They will tend to pick up water from here. Okay. They will tend to pick up water from here. But that water, they won't be able to carry for much longer distance. Right? The wind passes over. This water is then dropped. It will tend to return to its original position. By that point of time, the following wind will come. This wind, meanwhile, will pick up water from here also. That water will also be dropped. So, as a continuous consequence of this, of the rise and the fall of water in the same level here, which is happening, you will have a formation of vertical undulation. That is what is known as a wave. Okay, so here you have a distinct crest and you have a distinct trough. Okay, now after some time, the region crest will be represented by what? They will be represented by the water which is being risen up, which is being drawn up by the wind. Okay, so that crest is the area where the water for some temporary duration is driven up. After some time, this water will fall down as the wind passes away. So this will become the area of a trough, a crest, a trough, a crest, and so on. So that is why during the occurrence of the waves, you will observe there is no such forward motion of water unless and until you are standing at the coastline. If, let's suppose, ever you have taken a boat into the sea, you have moved into the sea, you would observe, or if you have seen the videos, whenever there is a large wave which comes, water rises up, falls down in the same area, again rises up and falls down in the same area. Water does not have a forward translatory motion unless and until you are in the coastline. Okay, so that is a wave. So here you will observe the water will rise up, will fall here itself, water will rise up, will fall here itself, again rise up and fall. So waves are defined as undulations, smooth movement of water in upward and downward direction of surface water, characterized by well-developed crest and trough. So here you will observe this is the motion observed in the case of water. So if I say that water follows a circular oscillatory motion as the wind passes by. That is during the wave movement of water particles. Why will the water go back in this case? Why is it that if you have a kind of the motion that we are talking about, why is it that here the water which has been brought up, why will it tend to go back in the first place? Very simple reason. Let's suppose the water has been brought up. Now there is a vacancy created here, temporary vacancy. As that water then drops, then it will push the water here to fill that vacancy, right? So it is about that filling of vacancy. that it moves up, goes down in the same area. But in the coastal area, you experience something different. In the coastal area, you experience these waves to bring water forward and then retreat as well. So when we talk about the coastal areas, there, what do you observe? So let's suppose this is the water. You will observe that the waves which are formed here, they will rise up, water will come, rise up, sink. By the time that you come closer to the coastline, you will observe that the waves, they build up and they crash to the shore. While there is a mathematical equation behind it, which includes the uh, wavelength of the wave, represented as lambda, and the depth of water, that is d, you take the factor of d by 2, depth represented by d. So if the wavelength is greater than d by 2, then the water will tend to move forward, but you don't have to indulge yourself in any of these mathematical calculations. Whenever I say mathematics, immediately the amount of panic that it creates is something uncomparable, so I'm not going to take you there. Just understand that in the coastal areas where the water is a bit shallow, where the water is not deep enough, as this accumulates, as the wind carries that water forward, this water will drop just like every other case. This water, when it drops, it is unable to come back because it will hit the sea floor, because the sea floor in this area is not very deep, it is shallow. So imagine if this is the sea floor, water is rising up, it has to go to a depth, but it hits the sea floor. Meanwhile, the other column of water has risen up. It will also accumulate on the sea floor. Meanwhile, the other column of water has also risen up by the wind. So what does that bring? That eventually will bring about a mounting of water and that forward motion. So this image that you see, which you have classified into as many details as maybe even I would not have thought while I was putting this image: tidal wave, wave accentuated formation of tides, this wave, that wave, fair enough. If you observe this wave, this is nothing but the piling up of water which is happening because the depth is not very significant. Okay. Now, here does not mean that it is so very shallow that I can also go there in my shorts and have a good time. Depth here is very much relative to what is the wavelength that is created by the water movement. So here, as this water tends to go down, it won't be able to sink completely because it will hit the bottom. And meanwhile, other waters are rising up and they are pushing forward. So like that, you will have this multiple piling up and that will bring the water forward. So in the coastal areas, you will have the waves bringing water forward, and then again that water will try to gain its normal equilibrium and will move backward. So that forward in coastal areas, forward motion due to lack of depth. So that forward motion towards coastline, that is known as swash. Very good. And then that retreat of that water back to the sea, of water back to the sea, that is known as backwash. Beautiful. Okay. So in the case of waves, for your examination perspective, all that you need to know is that these waves, there you don't have that forward translatory motion unless and until you are present at the coastline, right? Only there. Otherwise, you have a circular rotatory motion where the water keeps on rotating in that circular path. Okay, right? That mathematical formula would, okay. So forward motion, I will write it down, but let me attach a caveat, not very relevant for your, yes, only because you are curious, so I'll write it down. So for forward motion, lambda, which is the wavelength, it is less than d by 2. Wavelength of the wave d here represents depth of water. Okay, so if you want to apply the logic here, you will be able to understand. So basically, that is the case where it tends to move forward. Now, when we talk about tides, even though most of you said that it is one and same, tides are very different from waves. So what are tides? Tides are basically that frequent variation in the vertical height of the sea level. When we talk about the level of the sea, that sea level rises up and goes down. In most of the areas across the globe, this happens twice every day. Twice the water level will go up, twice the water level will go down. When the water level goes to the maximum extremity, that is the high tide. When the water level comes to the minimum extremity, that is the low tide. Okay, so basically here, when we talk about the tide, so let's suppose you have the water level here. So during some time of the day, you will observe, a couple of times during the day, you will observe that the water level tends to go higher up. So when the water level goes higher up, that is the condition of high tide. This is your normal level. And then twice a day, this will also happen, that the water level goes down. This is your low tide. So that is why this is also what is referred to as the high tide line, or HTL. Up till the portion where the water comes during high tide. HTL. This is your low tide line. That is why early morning, or sometimes when you go to the coastal areas early morning that you wake up, you will find that the regions very far from the where the sea is present, few meters far from it, you will have the evidence of moist ground. Means during the night, water would have come up till that level. Or if you are awake in the coastal areas during night, around 1 a.m., 2 a.m., 3 a.m. in the morning, you will observe that the water comes further inland because the water level has risen up. So why is that variation in water level observed? That twice a day, you will have the water level go up, and twice a day, the water level will go down as compared to normal. That is basically attributed to multiple reasons. You have the reasoning of the gravitational pull of the sun and the moon. And then you have the centrifugal force which acts on planet Earth. Both of them, they are responsible. So here, the vertical motion refers to the rise and the fall of the water in the oceans and seas. Due to attraction of the sun and the moon, the ocean water is raised up and falls down twice a day, and it is a periodic event. Okay, so you have these three factors which occurs. It is not because of upwelling. It is very different from upwelling. It is because of the gravitational pull. And if you have to think about the two major forces, so major forces are gravitational pull of the moon. One is the gravitational pull. Another is centrifugal force. So how gravitational pull of the moon and the sun? So basically, if you imagine here the presence of planet Earth having the oceans all around, uh, so basically, if you have the Earth, so we'll do this thing tomorrow. We'll complete or cover this portion tomorrow. You have the webinar also happening today. So we'll do one thing. We'll cover this portion tomorrow. We'll end the session here today. Why these pull is only in the case of water? That is because the land areas are too rigid. The gravitational pull of the moon will act even on the land areas, but the land areas are very, very rigid. So that is why they cannot end up moving, inflating, or deflating as a result of that gravitational pull of attraction. But when we talk about the water bodies, the oceans across the world, the seas of the world, they are more or less interconnected to each other. So when they get influenced by that gravitational pull of attraction, so maybe where the moon is, let's suppose if the moon is present here, let's suppose if the moon is present here, it will tend to pull. Let's suppose we consider this as the oceans, even though it is an exaggerated form, but it will tend to have a kind of a bulge here, right? That is what is known as a tidal bulge. Now, it cannot happen that that bulge suddenly appears. That water has to come from somewhere. So that would basically mean water from the surrounding areas are taken in order to supply that surplus. So that would basically mean that water from the surrounding areas, they are taken to form that surplus. And in order to gain equilibrium, there will be a counter bulge developed as well. So these two places will observe high tide, these two places will observe low tide. We'll study more about it tomorrow. And Saturday, we are going to have an extra session. That is when from 7:30 to 11, we will have the extra session. Why Antarctic is more saline than the region of Arctic? Because in Antarctica, that frequent melting and influx of river water is not there. In the region of Arctic, it is surrounded by land masses where various different rivers, they empty their water. So that reduces the salinity, along with very frequent melting of the Arctic ice on a seasonal basis also lowers the salinity level. In Antarctica, none of these factors are predominant. So we meet again tomorrow. Till then, do take care of yourself. Goodbye. Thank you.